we basically take a measurement, it's really important to not only put the number down, but to also make sure that you do put the units down. The units are almost more important sometimes than the number. The units allow everybody to really understand really what the number means, what it's in reference to. Again, a number just by itself really, has no sort of meaning in that sense. The other kind of important thing that we talked about was that when we do take a measurement, no matter what type of measurement we take, there's always some degree of uncertainty associated with that measurement. Um, there's some degree of estimation that has to occur when somebody takes a measurement. Um, and the degree of sort of that estimate that you have to make is really dependent on the equipment that you are using. So as we talked about last time, it's really good to, for the most part, look at the scale that you're using on a particular piece of equipment. For example, if it's a ruler, if it's a graduated cylinder, it's got some type of markings basically on it. We oftentimes want to figure out what does those smallest markings mean. We also want to figure out obviously what the bigger markings mean as well. But as we saw, you could usually go one more place to the right of the smallest marking, not in 100% of cases, but usually you could take the reading to one more place to the right. And that's really important because what that means is when we take a measurement, you always want to record all the certain numbers, as we talked about. All the certain numbers basically mean no matter who kind of takes a peek at it, takes a look at whatever you're measuring, everybody should almost agree that, hey, this is at least, 2.4 centimeters or something like that. But maybe it's not exactly 2.4 centimeters. Maybe it's a little past it. Maybe it's way past it and stuff like that. And that's where the degree of estimation basically comes into play. Um, I may look at something and go, hey, I think it's like right between the two markings. I think it's like halfway there and maybe record it as a 5. Maybe somebody else may look at it and go, I think it's like way closer to the other next biggest marquee and record it maybe as an 8 or a 9 or something like that. So when we do take a reading, we always record all the certain numbers plus that first uncertain number. And those are what are basically considered significant figures. So significant figures are really important. They are pretty much telling people when we took this measurement, I think we could definitely read it to here. And that last number there is a little bit where that uncertainty lies, but it shouldn't be that far off. And that's why we also talked about that it's really important when you do take a measurement that you don't get rid of numbers, even if you feel like it's right on a line and you have the ability to take it, say, to 2 decimal places, you should take it to 2 decimal places and just put a 0. So as we talked about last time, if you're measuring something, and let's just say it's like a ruler, maybe a draws, there we go, and this is like 2 centimeters, and you feel like, hey, that's like right dead on, and there's a bunch of little markings down the road here, and you would want to record something like 2.00 perhaps, because you have the ability to go out to here, and that's where that uncertainty would sort of lie in that particular measurement. When we talk about the uncertainty, and this is also an important point, the uncertainty lies in a measurement not necessarily with the last number that's written, but it does lie with the last significant figure that is written. So that's a really important sort of aspect of it. Sometimes people think it's always going to be that last number is sort of where the uncertainty lies. And it's not necessarily the last number, but it is the last significant figure is where that uncertainty lies. So there is sort of a difference on that. We talked about how to count significant figures. So some of the rules we sort of ended with last time was pretty much any number that is not a 0 is a significant figure. So if you have a number that's obviously not a 0 starting to count from left to right, that's where you should start counting your significant figures. If you have a 0 that comes at the beginning of a number before you hit the first non-zero, those are not significant. So again, left to right, we have zeros, not going to be significant till we hit the very first non-significant non-zero number, and that's where we should be counting. If we have zeros that are in the middle of two non-zero numbers, those zeros are significant. And the one that gives people usually a lot of trouble sometimes is the zeros that come at the end. If we have zeros that come at the end of a number, they may be significant and they may not be significant. And what determines whether or not really they are significant is there a decimal point in the number? The decimal point doesn't have to be right next to the zero, but it just needs to be somewhere in that number. So again, a couple examples I think we closed on were these two down here. I think we had 400, for example, written like this. We also had 400 written like this. Again, with the decimal point here, these zeros at the end would make those guys significant, and this guy would technically have three significant figures. While with nothing written here, just put like a circle, nothing written there in terms of a decimal point, these zeros are not going to be significant, which means in this case, we have one significant figure. And as we talked about at the very end, when we talk about the level of uncertainty in this measurement, the one on the left, the uncertainty lies in the ones place right here, which as we wrote over here means technically, you know, this measurement may be somewhere around 401, maybe it's something like 399. While over here where we have one significant figure, the uncertainty really lies in that first digit there, which is the hundreds place. And that means that the measurement may be 500 or may be somewhere near 300. So much bigger span in terms of where the uncertainty in that measurement lies, again, because it has only one significant figure. Any questions on that stuff we talked about last time there? Okay. So here we have some numbers here, as we talked about. Again, if it's a non-zero, they're going to be significant. So this measurement here, again, starting to count left to right, that's two significant figures. Here we would start counting here. Everybody's a non-zero, so that is five significant figures. Looks a little messed up on the screen here. So I'll just go with this number here that I can read. So here we have some zeros that are trapped. We have our 2, and then the 0 in the middle is significant. So that's the second significant figure, and that would be the third significant figure. I'm not really sure where that all went. So we'll just go down here. This guy here, 0 at the end, it has a 5 and nothing written. So we assume it has one significant figure, which is that first one. This guy here has the zeros at the end, and that means that those are going to be significant because of the decimal point. So that 1 is significant, 6 is significant, and the two zeros at the end are significant, which gives you 4 significant figures. The stuff that I think that moved around, I'm not sure where it is, but when we do write a number in scientific notation, which is this 5.40 times 10 to the fourth, or maybe 3.2 times 10 to the minus 2. This is numbers that are written in scientific notation, which we sometimes will use for large numbers and small numbers. But in terms of significant figures, the rule is when you write a number in scientific notation, such as what we have here, all the numbers that come before the times 10 part are always significant. So this number here would have 3 significant figures. This number here, which is 3.2, is our number that it comes before the times 10 part, would have 2 significant figures. So when we do write a number in scientific notation, it basically is a number between 1 and 10. And so that's basically that big N number. And then we have times 10 to the N, and that could either be a positive number or a negative number, and depends sort of which way you move it. So if we had something like, say, 3, 2, 5, 6, and we wanted to turn it into scientific notation, we would assume that the decimal points here, even though it's not written, we would go 1 place to the left, 2 places to the left, 3 places to the left. And that gives us a number that's between 1 and 10, should not be 10 or higher. So that's 3.256. And we did go 1 place, 2 places, 3 places to the left, times 10 to the 3. And that would be the proper way to write that number in scientific notation. Significant figure-wise, if we look at the original number here, it has 4 significant figures. When we convert it, that is why we kept all the numbers there. That also has 4 significant figures as well. So as you go from scientific notation to decimal form, are back and forth, you never want to lose any significant figures. So for example, if we have 320 written just like this without the decimal point there, it actually only has, again, 2 significant figures here. This 0 here would not be significant as there's no decimal point. And if we were to do that into scientific notation, 1 place and 2 places, we would write 3.2 like we have above there, times 10 to the 2. Again, 2 significant figures here, 2 significant figures here, and we want to maintain that. Now, if we had a small number, 0.0503, to get this to a number between 1 and 10, we actually have to go to the right 1 place and 2 places. This number here has 4 significant figures, which means we should end up with 5.030 times 10 to the minus 2 because we went to the right. So negative exponent for smaller numbers, larger numbers, positive exponents, but 4 significant figures here, and obviously 4 significant figures there as well. Any questions on that? So here's some more examples. Again, starting to count here. First significant figure, second, third, and fourth significant figure. Starting to count here, significant, significant, so that's 2. Counting here, everybody's a non-zero, so that's 3. And again, counting here, everybody's a non-zero. That would be 5 in that particular case. And again, our zeros between, so starting to count here, significant. These are where sometimes referred to as trap zeros, so they're significant as well. And that would be significant there for our fourth significant figure. This would be 1 significant figure, 2 significant figures, 3 significant figures. These zeros that start don't count. We would start counting right here, as that is the first non-zero number. The 7 would be significant, the 0 there would be significant, and the 2 would be significant, giving us 3 significant figures in this number. Same thing here, we would start, and this 0 would not be significant. This is our first non-zero number. That's where we would start. 0 is trap, so significant. That's 2, 3, trap 0, 4, and guy at the end there, 5. Any questions on counting those? Okay. And here's our zeros at the end. Again, some people may say it's ambiguous because there's no decimal point here, but again, we'll go with 1 significant figure here, as there is no decimal point. And in this particular case, it would have 4 significant figures. All these zeros are going to be significant because there is a decimal point in this number. And again, the level of uncertainty is the place of uncertainty in this top digit is right there. So that's the uncertain digit. While in this last one, the uncertain digit is over here. So this is a good demonstration, as I was talking about a second ago, that the level of uncertainty, or the place where the uncertainty is not necessarily the last number, but it is the last significant figure. So again, on the top one, the 2 is the last significant figure. So that's where the uncertainty is, while the 0 on the bottom here is where our uncertainty would lie in that particular case. Any questions on that there? And again, our zeros at the beginning are not going to be significant. So this is where we would start counting. 0 at the end would be significant. Again, doesn't need to be near the decimal, but it's there. And that is 3 significant figures right there. This would have 2 significant figures, starting with the 2. And this guy would have 1. Again, none of these going to be significant. Don't start counting until you hit that very first non-zero. Again, kind of like placeholders. And again, Here is two significant figures. These will not be significant as there's no decimal place. That means, again, where the uncertainty lies in this measurement is actually like right there in that digit, which means, again, this could be something like 45,000, maybe 43,000. And again, that is the level of uncertainty at that digit, the thousands place, basically. This is 810, again, significant up to the 1, not going to be significant here because there's no decimal point. So we have 2, and here we should have 3, which would take us to the 5. None of these zeros going to be significant. Again, if they wanted the decimal there at the end, they would put it. So since they did not put it, you could assume that those zeros will not be significant. So sometimes people go, well, isn't just assume that there's a decimal here, even if they don't write it? And, most people sort of assume that. But in case of significant figures, if they don't put it there, then we're going to assume it's not there. And again, without it, there would be two significant figures. If they wanted it, because you could do that measurement, they would put it there. And then it would become 3 significant figures if it was written such as this. Any questions on that? And again, as I mentioned before, our scientific notation, those are going to be numbers where when we do write in scientific notation, it always are going to be significant. So all 3 of these guys before the times 10 part are going to be significant. Same thing here and same thing here, which gives us our 6.0330. By the way, if we were going to turn this into a decimal, we would take our 6.0330 and we basically go 5 places. As a negative, which means we want to make it smaller. So we would want to kind of go this way, to make it smaller. So we would end up with 0.000060330. And again, you could check yourself by going the other way. 1, 2, 3, 4, 5. And this would be the correct way to turn that into a decimal. Again, here having 5 significant figures. If we were looking at our number in decimal form, we would not start counting until right there. And then that 6 would be significant, 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 and significant. So again, we never want to lose any significant figures as you go one way or the other. You want to always make sure that you do maintain them going forwards and backwards. Any questions on that there? While we're talking a little bit of scientific notation, which I think was in sort of chapter 1 as well, which I think some I covered last time, but let's just make sure, since we're all together here, a reminder, more importantly for scientific notation, you want to make sure that you do know how to write it. And as I mentioned, it does have that general form of n times 10 to the n. And as I mentioned, that is our number between 1 and 10. And again, a positive or negative number, depending on which way you kind of move it, to get to a number between 1 and 10. But more importantly, when we use our calculator, we do have exponent buttons. So that is the EE button on a lot of calculators. That is the EXP button on a lot of calculators. And some of the newer ones, and by that I mean usually the calculator will also have somewhere in there like a little circle sort of selector type thing in the middle. They might have a times 10 to the n type of number as well. So you want to make sure that you do use your exponent button when you punch a number in scientific notation. Yeah, let me talk about that before we get to the calculator part then, just to make sure. Let's see. So in terms of positive or negative, it really depends on which way you're moving it. So if you have a number that's in decimal form, if you will, so say 125.1, and you want to turn that into scientific notation. When we look at this number, it's basically a number above 1, so it's kind of a large number. So we need to move the decimal until we get to a number between 1 and 10. So we go to the left, we go one more place to the left, and that would give us 1.251 times 10 to the 1 and 2 places. And we can see what we get in terms of the exponent is actually a positive exponent because we started with kind of a big number, if you want to think about it that way. So if it's sort of a number above 1, or, I'll call it a biggish number, we usually should end up with a positive exponent because we moved to the left the decimal point. So we moved it to the left, ends up with a positive number. Now, if we're starting with a small number like 0.000122, in order to get us a number between 1 and 10, we got to move that decimal now to the right. If I move it here, I'm at 0.0012. If I move it here, I'm at 0.012. If I move it here, I'm at 0.122, which is close to a number between 0 and 1.22. But I do need to go right here, and that is 1.22. And that would give me 1.22. That also is a very small number to begin with. So that should have a negative exponent when we move it to the right. And we moved it, I lost track there, 1, 2, 3, 4 places. So we moved it 4 places. So when we have to move the decimal point to the right, we will end up with that negative exponent. And basically a small number, anything less than 1, is sort of what you want to kind of think about. So anything above 1 should end up with a positive exponent when you write in scientific notation. Anything with less than 1 should end up with a negative exponent. Questions on that there? Okay. So getting back to sort of the thing, getting back to the calculator, which is really important, is to make sure you know how to sort of punch these into your calculator. So when we punch a number such as, say, this guy right here, 4.9 times 10 to the 3, when we put it in our calculator, you typically want to punch in 4.90, and then you want to hit your exponent button, especially if you have the EE button or the EXP, one of these type of buttons. And you don't want to hit anything other than that button. So you don't want to hit the multiplication button. You don't want to hit anything else other than that button, which is that. And what it typically will put up on most people's calculator is 4.90. It will put an E, or maybe go like 4.90, pop up a couple of zeros or something like that. When you hit that E, this button basically stands for the times 10 part of the number. So it stands for basically this part of the number right here. So what's left to put is really just the 3. So you would hit 3 and it would do that. And then it probably would turn this into a 3. And that would be the proper way of punching in a number in scientific notation in your calculator. You should not be hitting the multiplication button. You should not be hitting the shift or second or log button or anything like that. This is how you should properly do it. If we had a negative exponent, like say this guy here, you would go 8.0. Again, you would hit your exponent button, one of those two. You then would want to hit your negative button, which may look like that, may look like this, and it probably will do something like 8.0. Again, put the E, 8.0, maybe pop up a couple of zeros. And then what's left is 3. You would hit 3. This would go -3, and this would change into a -3. So this is definitely how you want to put these numbers in. Again, people always want to do like extra multiplication buttons and subtract buttons instead of your negative buttons. So you want to make sure that you use sort of the right thing. Now, in terms of if you have sort of a newer calculator, they kind of sell these days. And basically, you do have to put it in a certain way because of the way it's programmed. So it's not necessarily maybe your fault, but it is sort of the way the thing is programmed that sometimes it's very hard to do that. Yeah. So if you don't see an EE button, you don't see an EXP button, you probably will have a button that kind of looks like this guy. And on your calculator, you'll probably have like a little, almost like a control pad type button, like an old the Game Boy type button that, you know, you could kind of push a circle sort of thing. So you'll have that type of button on there, and you'll have this button. And that actually is your exponent. But the way these sort of newer calculators are programmed that has that button, that times 10 to the n button, and again, typically those guys will have this kind of circle in it, almost in the middle of the calculator. You got to put parentheses around all your numbers that you put in scientific notation. So let's just say we were doing this guy here again. You would have to type 8 point, actually you got to start with a parentheses first. Then you got to type 8.0. You then will actually hit this button, and it will probably will on your calculator put like a 10 and an N. And what will happen is the cursor will end up like up on top, kind of blinking. And then at that point, you could hit your negative button just like before. And when you do that, it'll make that thing look like 8.0 times 10 to the negative, and then you can put the 3. And then what you'll still have at that point is your cursor is way up here. And you then got to go to this circle thing, hit the right-hand side. And what that will do is bring your cursor down, and you could close the parentheses. So if you have sort of that type of calculator, you got to kind of follow those steps. You got to go parentheses. You got to hit the number that you need. You got to hit that times 10 to the n number. Got to hit the negative number. You then got to hit whatever number you want. Then you actually got to hit that circle guy to bring your cursor back down and close the parentheses. So it's perfectly fine to have a calculator like that. A lot of new ones do it. But just the way they sort of been programming a calculator like that, the way they program a calculator like that, it's just if you don't put the parentheses around all the numbers, you'll be in trouble. What you should not do on any calculator, including the one I'm describing, is you should not go to the top and hit the second or the shift button, which is most calculators are in the upper left. And you should not go to the log button where it says 10 to the x and do that combination. That is not doing scientific notation, and you will get the wrong answer. So you should not be doing any of that, nor should you be doing anything that involves a multiplication button when you're just putting a number in. So you don't want to do any of those things. Otherwise, again, you'll get sort of the wrong answer. So what a lot of people do for scientific notation is they use that shift button. They go to that log button because it's got the 10 to the x, and that's sort of how they do it. And that's not really the right way to do it. It's just to be careful on that. You don't really want to do that. All right. So again, play with your calculator. And if you're having trouble, you know, during discussion or something, we could probably figure it out. I could look at your specific calculator. Obviously, there's probably 500 different models, but we could probably figure it out during discussion if you need help. The way you'll know as we start maybe doing some calculations that you're having trouble is when you get an answer. Your answer will look very close to the right answer. So you'll get an answer maybe in scientific notation where you have 1.25 times 10 to the 2 is the answer, and then you got the 1.25 part good, but this part of your answer is not so good. And that's usually an indication that you're not punching it in correctly. So while we're talking about calculators here on a tangent here, why don't we try just one here just to make sure. Why don't you take 3.25 times 10 to the minus 9, and why don't we divide it by 1.2 times 10 to the 16 and see what you get. I'll do it as well since I just made it up. So again, if you're going to punch it in 3.25, you want to hit that exponent button. You want to hit the negative button in 9. Then you want to hit your divide button, 1.2. Exponent button, again, I didn't do any multiplication button or anything like that, and 16, and hit equals. And I think you'll end up with something like 2.7 times 10 to the minus 25 as your answer in that particular case. So you want to make sure, the other thing that sometimes people do is, for example, on my calculator, It says 2.708333333 E minus 25. Some people's calculators at the very end may say 10 to the minus 25, very small. You don't want to forget that part of the number because that part of the number is important when you write it. Sometimes people just write the front part and kind of forget the exponent part. So you want to make sure that you definitely double check that you're not missing an exponent. All right, any questions on that there?
So we would only need to write the 2.7, like the 08333.
You actually would. The 2.7 is actually the right answer here. We're going to talk about it in a few slides down the road. But when we do a calculation such as this, we're multiplying. So this has 3 sig figs. This has 2 sig figs. So the answer should end up with 2 sig figs. And we'll talk about that in a few slides down the road, I think. Yeah.
Oh, thank you.
You're welcome. Other questions? Okay, so get back on what we were talking about here, which is our significant figures. Again, with that decimal point there, this has 3 significant figures. And again, we do want to maintain it when we write it in scientific notation. This guy, again, has 1 significant figures. So we can get rid of all these zeros, and we should when we write it in scientific notation. So written like that, it has 1 significant figure. And this guy has 2 significant figures and also has 2 significant figures over here. So we always want to maintain that. Again, if you by some chance wrote 4.00000 times 10 to the 5th, this guy now would have all those being significant, which would be 6 significant figures, which is not what the original number has. So you don't want to gain significant figures when you go from scientific notation to decimal, or lose them as you go the other way. Other questions on that? Okay. So take a second and identify, let's go with how many significant figures are in each of those. So take a second and we'll talk about it. Okay, so let's take a look. Again, starting on our first one here, all these zeros are not significant. They're leading zeros. So we start counting here. That is significant, that's significant, that's significant, and that's significant. So this guy has 4 significant figures, with the uncertainty in that last significant figure, which would be there. So that's where the uncertainty lies. Coming to B, right here is our first non-zero. So that's where we'll start counting. That is 2, 3, 4, and 5. So this would have 5 significant figures, with the uncertainty also lying in the last significant figure, which would be that 6. Now, lastly, this is where we would start counting. That's 1 significant figure. That 0 is trapped, so that's significant. Significant, significant. These zeros at the end are not significant as there's no decimal point in there. That means that this number here has 4 significant figures. Now, the uncertainty in this measurement is not the last 0. It is actually the last significant figure. So that 4 is actually where the significant figure lies, basically. Any questions on any of those? Or the uncertainty is in that last significant figure.
Is the uncertain number the same as the estimated number?
It is. So I sometimes call it uncertain number or estimated numbers. It's all the same. Yeah. So when we look at that last one, that 10440000, because this is technically our last significant figure, and as we talked about, what we record when we take a measurement is all the certain numbers plus that first uncertain number. So this is where that first uncertain number would lie, which is basically where that estimate was made, which meant in this measurement we could get as close as, maybe it's like 5 at there, or maybe it's like 4 or 3, 0, 0, 0, and 4, 0, 1. So that's sort of where the uncertainty lies, is in this digit right here. The thousands place basically is where that uncertainty lies. So sometimes people, like I mentioned before, always think, oh, as much the uncertainty or the estimate, it's got to always be that last digit. And it's not always the last digit in a measurement, it's the last significant figure. So that's an important sort of distinction between the two. Other questions on that? Okay. So that's what we just went over. There we go. Now, there's also some numbers which are considered exact numbers, and exact numbers basically happen one of two ways. Pretty much they are things that are counted. So if I had, for example, like the picture shows, two baseballs sitting on the floor there, I'm not going to find some really scientific way of figuring out how many, how many baseballs there are. I'm just going to pretty much count them. There's two baseballs. So those are an example of an exact number. And another example are definitions. So for example, 1 foot is 12 inches. So that's a definition or equality. 1 kilogram equals 1,000 grams. Those are basically equalities. Those are considered exact numbers. 1 inch is 2.54 centimeters. So that's also, an equality or an exact number. What's the deal with exact numbers? Well, exact numbers have really unlimited numbers of significant figures. You can pretty much give them as many significant figures as you want. And more importantly, when we do calculations involving significant figures, we don't look at exact numbers in terms of how many our answer should have. So if we have an exact number in a calculation, we pretty much ignore it in terms of how many significant figures our answers should have. So here's some examples of exact numbers. And so you can see these are all metric ones, and we have our US system, which is sort of the English system of stuff. And these are all equalities. We have 8 donuts, 2 baseballs and so forth. These are all counted things. These are defined equalities, and they're all considered exact numbers. Now, we talked about 2 systems of units earlier, which is really the metric system and kind of the US system, or the English system, sometimes referred to. And for the most part, for sure, if it's a metric to metric equality or a US to US equality, it's really considered an exact number. When we cross over and have like a metric to US type of equality, sometimes people will not consider those exact numbers, and you will have to sometimes worry about significant figures and those things. So for us, we're not going to worry about that. So what I mean by that is, even if it's a sort of crossover metric to US, like grams to, say 454 grams is a pound. We got metric, we got US measurement. We're going to still consider that an exact number. So anything that's an equality, we're going to consider in this class an exact number, which means it could have really unlimited number of significant figures and will not affect your calculation. I will just put that little side note that some people will say, if you're kind of crossing over metric to English or metric to US sort of conversion, you shouldn't consider an exact number, but we're going to consider that type of thing here. So pretty much anything that you use as a conversion factor, anything that you use that's an equality in this class, we will consider an exact number. But again, just be aware, some people may not agree 100% of the time doing that. Any questions on that? So let's see. We want to know these measured or exact numbers, and give the significant figures. So if we have 3 coins, probably that would be a exact number, right? If you have 3 quarters sitting on the desk, you would most likely just count them. The diameter of a circle is 7.902. That is definitely something that you would measure. And since it is a measurement, starting here, that would be significant. All these numbers are significant. So that would be 4 significant figures in this particular case. 60 minutes and 1 hour. That is an equality, right? These 2 things mean the same thing. They're just on different scales. So that would be considered a definition and an exact number. Any questions on that there? So let's try this. Figure out how many significant figures are in each of the following. So take a second and see what you come up with. Okay, so let's take a look again. These zeros here are leading zeros, so they're not significant. This is where we would start counting. And this last zero is going to be significant. Again, there's a decimal point in here. So this guy should have 2 significant figures. With the uncertain digit or estimated digit, that last zero. Coming here, this would be our first significant figure, second, third, again, the zero at the end going to be significant because of the decimal point, doesn't have to be near it. And that would be 4 significant figures. Again, the uncertainty lying here, or the estimated digit lying there in that last zero. All these zeros coming through here are not going to be significant until we start counting here. So that would give us obviously only 1 significant figure, where the uncertain digit or estimated digit would actually be right here. And lastly, that's significant. That is significant. 0 at the end going to be significant, again, because of the decimal point. And again, the uncertainty lying here. And that would give us 3 significant figures. Any questions on that there? Okay. All right, so let's try one more here. So for each of these, figure out the first one, which one has 3 significant figures, and then which one all the zeros are significant and how many that one has. So if I'm maybe I want to make sure I'm understanding your question. So 0.08 centimeters, this would be our estimated digit. So if you're asked maybe in the lab how you would display that, I would probably take the 8, but you might want to write 0.08 and maybe just circle it or put a line next to it so she's the one grading it, so she knows it's that 8, if that's your question, if it's more like how to put it for the lab. I personally would probably be okay if you put the 8, but again, I'm not the one grading it, so you want to make sure that, however you do it, maybe just make sure you signify as that, especially if it's some number that maybe has a lot of zeros in it. You just put 0, it's not really sure which one you might be talking about. So maybe just rewrite it, put a line over it or circle it or something like that. Okay, so let's take a look here. We want to know on the first one, which one has 3 significant figures. So looking at this first number here, this guy has starting here 1 significant figure, 2, 3, and this 0 is going to be significant because of the decimal. So that's 4, so that's not it. The second one, these zeros are not significant, not significant, not. We would start counting here at the 4. Then we got 7 and 6. So this guy here, all 3 of these are significant. And lastly, we have a number in scientific notation, and everything before the times 10 part are going to be significant. So that would be 4 significant figures. So it looks like 2 there for the first one should be the correct one. The next one, we want to know which one are all the zeros significant. So starting here, these zeros are not significant until we start at the 3. Then this one is, and this one is. So this has 3 significant figures. But these guys are not significant, so 1 wouldn't work. This is significant here. Significant, significant. Zeros at the end are going to be significant because of the decimal point, which means all the zeros here are significant, and also means this has 5 significant figures. So 2 would work here. And lastly, all these numbers before the times 10 part are going to be significant. So this has 4 significant figures. Also, all the zeros there are going to be significant. So in the case of B, both 2 and 3 contain numbers where all the zeros would be considered significant. Any questions on that there? That leaves us obviously the last one here, where we have 5.80 times 10 to the 2. 5.80, again, written in scientific notation, means that all 3 of those numbers are going to be significant. and we should have 3 significant figures. Any questions on scientific notation, sig figs, how to count them? By the way, sometimes the only way to get a number to the right number of significant figures is to write it in scientific notation. Other than that, if it says to write in scientific notation, you should. If it doesn't state it, you could write it in decimal form or scientific notation, but as long as you have the right sig figs, you're good either way. It doesn't really matter. So you don't always have to write a number in scientific notation. The only time would be obviously, if it specifically says to do so, you should. Or you're welcome to do that. You don't necessarily, you can write every number in scientific notation if you like. Any questions on any of that there? Okay, then let's talk about a question that was asked a little bit earlier, which is, what do we do with calculations and significant figures? And a reminder that when we do use a calculator, that doesn't always give us our answers to the proper number of significant figures. So basically, there's kind of two sort of sets of operations that we typically do. We typically will either multiply a number or divide. And basically, when we multiply or divide a number, the number of significant figures in the answer equals the number of significant figures in the number with the least amount of significant figures. So when you're multiplying numbers, say 3.25 times 1.2 times 3, 2, 4, 5, 6. Forget about the answer, but if we were doing multiplication here, we would look at each of these numbers and we would want to know we are multiplying, so we're interested in significant figures here. So if we look at the first number, it has 3 sig figs. We look at the second number, it has 2 significant figures. We look at the third number, it has 5 significant figures. The smallest number of significant figures in all of those guys is 2, which means when we get our answer, we should end up with 2 significant figures. So when you multiply or you divide, you want to find the number that has the least number of significant figures, and that is what your answer should have in terms of significant figures. Question on that. The other sort of group of stuff that we do is we either add or subtract. When we add or subtract, the answer should have the same number of decimal places as the number with the least number of decimal places. So when we add or subtract, we're not looking at significant figures. We're looking at decimal places. So like 3.255, 1.11, 1.0, for example. And if we took all those numbers and we added them, and give it a temp without the calculator. So that's a 5. That's a 6. That looks like a 3 if I wrote straight. 3, 4, 5. So we get this number here on the calculator. And it may not give us the right answer in terms of significant figures. So when we're adding, we're not looking again here at significant figures, but we're looking at decimal places. So this number has 3 decimal places. This number here has 1 decimal place. And this number here, I'm sorry, 2 decimal places, so learn to count. And this number here at the end has 1 decimal place. That means our answer actually should go to 1 decimal place. Now, we would round as well. So we would look at the number next to it, which is a 6. So we would round to 5.4, which has 1 decimal place. But by the way, it has how many significant figures? It has 2 significant figures. Yeah. So adding and subtracting, we look at decimal places, the one with the least. Multiplying or dividing, we look at significant figures, also the one with the least. And the reason we always look sort of for the one with the least is that is pretty much your worst measurement, if you will. So the best you could do if you're sort of taking a bunch of numbers and you're multiplying, dividing, adding, or subtracting a bunch of measurements, the best you could do in terms of sort of accuracy or precision is your worst measurement. This guy is really our worst measurement because we were only able to go to the 10th place. While over here, this guy also was our sort of our worst measurement. We were only able to go to the 10th place. So we go to the smallest because it's sort of our worst measurement. And that's what limits how good of an answer we could basically put there. To answer the question is yes, you should always round to the right number of significant figures. And that's what our next slide is. So that's a good question. So we do always want to round our calculations to the proper number of significant figures. And by the way, when we're talking sort of about calculations, we'll see it here in a second. If we're doing multiple types of calculations, so in a process. So for example, let's say we had 3.256 times 1.2223, and we divide it by like 12. So if we were going to do all this just in terms of sort of significant figures, we typically would do the part in parentheses first. So we're multiplying, which means we want to look at sig figs. So the top one here is 3.256, which is 4 significant figures. The one next to it is 5 significant figures, which means technically speaking, when we get the answer for the top part, our top part should have 4 significant figures. We then would be taking that top number and dividing it by the bottom number, which has 2 significant figures, which means when we're all said and done with our very final answer, it should actually end up as 2 significant figures. So sometimes, and it's very common in chemistry, there's a lot of sort of math that you do. There's a lot of steps along the way. And you do want to keep track of what is happening and make sure that you round to the proper number of significant figures. I will put it this way. If you're doing multiple steps in a calculation, and let's say you get an answer and then you need that answer to go to the next one and you do another calculation with that number, you get an answer, you take it and do the next part of the calculation. You do want to avoid rounding a lot until you get to the very end, because every time you round a little bit here and then you take that number and get an answer, round a little bit more, round a little bit more, you will find yourself moving a little bit further and further away from the correct answer. So it's always a good idea to not round a lot until the very end and kind of clean it up as the very end. So for example, here, if I did this one, I put in there and I made up the numbers. On top, I would go 3.256. I would times it by 1.2223. And, you know, I get a number that is on my calculator, you know, 3.9798088, which obviously is not rounded to significant figures. I personally would not necessarily round this number right away to 4 significant figures like it should be, you know, which would take us to here. Sometimes people will put a line just to keep track of where the significant figure is. And then I would take that and whole number on my calculator and just hit divide by 12. And at this point, I get a number like 0.331650733. At this point, I know that my final answer should be 2 significant figures. Again, that would take me right here, and we should round to 0.33 in this particular case. So you should try to avoid sort of a lot of rounding along the way, especially if you're going to use that number in multiple calculations in a row. If you're just going to do one calculation, you're done, then you should round. But if you're going to take that answer and continue on with it, you should really avoid rounding until you get, you know, kind of to the end. you should kind of keep track of everything as you're going through it. Question on that there. So what are the rules of rounding? Well, they are the regular sort of rules. So if it's 4 or less, you could drop everything else after that. If it's above 5, the next number, then we go up by 1. You do want to avoid rounding, like I said, in each of the individual steps. You also want to avoid crazy rounding and stuff like that. So let's say you had a number like $13,333 or something like that. And let's say we wanted to round to 2 significant figures. Take a second and think about what that answer would be. We'll talk about it here in just a second. So what would it be if I took that? A few different answers. So let's talk about a couple of these here. So if we go 13, that is 2 significant figures. I also think saw 13,000. And if I wrote it like this also is 2 significant figures. So both of those have 2 significant figures. So which one should be the right answer? So the right answer is actually this one here. That is the right answer because although the 13 does have 2 significant figures, it does not mean the same thing as what we started with. So what I mean by that is if I owed you $13,333 and I said, hey, I'll just give you 2 significant figures. Here's $13. We're all good, right? That's about the same thing. So for example, if this was dollars, there's a very big difference between $13, I might not get out of the room, and $13,333. There's a very big difference. So although it does have the right number of significant figures, you've changed the meaning of what your original number is. And when you round, you never want to change what the meaning of your number is. You want to be able to sort of maintain that. So by writing it like this with no decimal at the end, that is 2 significant figures. And if we took $13,000, maybe give me the nice teacher discount there of $333. If I give you $13,000, it's pretty close to 13,333. It's in the same ballpark. So you never want to do any type of weird extreme rounding again. And it happens. People are so focused on, I got to get it to say 2 significant figures that they just start lopping off numbers and stuff like that to get it to the correct number. But you might actually change the meaning of it. So you never ever want to round and change the meaning. You want to maintain what the number means and also have the right number of significant figures. Another way we could have done it as well would be 1.3 times 10 to the 1, 2, 3, 4 places. This would be it written in scientific notation. It has 2 significant figures, which is why I dropped out all of the zeros, because if I did this, this now has 5 significant figures. So again, you could definitely go scientific notation if you wanted to as well. Question on that there. Okay. So here's some examples like we've been talking about. We want to go to 3 significant figures. Again, we would go to here. We would look at this number, which is 3. We drop the rest of it and end up at 8.42. If we want to go to 2 significant figures, we would look at the 2 and drop it. We want to go 3 significant figures goes here. We would look at the 8. It would round up. So that's how we got to 14.8. We want to go to 3 significant figures. We would look, goes to here. We would look at the 6. Also would round up. And we would get something like 3260. Again, you see no decimal point written here because that would turn it into 4 significant figures. Or again, as we just talked about, you could write it in scientific notation as well. Any question on those? All right, so take a second and write those guys rounded to 3 significant figures. Okay, so 3 significant figures would take us to here. We then would want to look at that number there, and we would want to round up in this case, and that would take us to 3. Whoops, we're right, 3.15 on the round up. 2 significant figures would take us to this digit. We would look at this guy. It's less than 5, so we would drop the rest of it and should end up at 3.1 there. So looking not too bad, I think, in there. So we would go 3.1 in this particular case. Again, in that case, we just drop off the rest of the numbers for this guy here. Any questions on those two? Okay. So why don't you do this, adjust these to 3 significant figures. While we're at it, write this guy in scientific notation. And also write this guy in scientific notation as well. So write those 2 in scientific notation after you round it to 3 significant figures as well. So do both decimal form and scientific notation for the first 2. Okay, so let's take a look. So we want to go 3 sig figs. So always starting left to right. Third significant figure is right there. And we then want to look at the next one here, which is a 7. So that means we are going to round up. So in decimal form, if you will, I guess, or 825 centimeters. We wanted to turn that into scientific notation. Again, not written here, but assume that the decimal is there. So 1 place and 2 places. That would give us a number between 1 and 10, 8.25 times 10 to the 2. Again, big number, positive exponent in this particular case.
I have a question on that one.
Yeah.
We wouldn't put a decimal behind the 5 on 825 when we're just for the significant figures.
You don't have to in this particular case. You could technically, it would be the same. For example, if you did 825 and you put the decimal there, centimeters, it would still it really would still have 3 significant figures in that case, unless you specifically then put a 0 or something there. So you don't necessarily have to in this particular case because they're all kind of non-zero numbers. So that will maintain basically the 3 significant figures by having it there. If you were rounding in a different problem, say, and it came to like 820, for example, and you wanted that third significant figure, you then would have to put the decimal there in order to get it to 3 significant figures. R has to write it in scientific notation, like this. So because really this last digit wasn't a 0, and that's sort of where we're ending it, you didn't really need to put the decimal there. If you did, it really wouldn't be any harm as long as you didn't like add the 0 like I had there originally, because then you would go from 3 significant figures to 4. Other questions on that? Okay, so looking at B, 30 significant figures would take us here. Remember, this 0 is not significant. So we would start counting here at the 1, and that brings us to the 2. Looking at our 4, it is less than 5, so we would just drop it, and we would end up with 0.112 grams in this case. If we wanted to write in scientific notation, taking the decimal to the right in this case, it was a smaller number to begin with. So 1.12 times 10 to the minus 1. And again, maintaining our 3 significant figures there, and obviously our 3 significant figures there. Any questions on those 2 there? Now, this last one here, It's a good question, and the answer is so I think you're asking, do you have to put this 0 here? And the answer is no, technically you don't have to, but it is really proper, especially in science, that if you have a decimal like this 1, 1, 2, to actually put the 0 in front of it. And it's really for when you maybe take this number and you start doing a bunch of other calculations where maybe you got numbers that are just decimal numbers or something like that. What ends up happening if you don't have sort of that 0 there to break it up, sometimes people see these numbers running together. So it's really good practice to always kind of put that 0 in front of the decimal. And again, it just sort of acts as a placeholder. It actually acts to sort of keep everybody's numbers sort of separated and stuff like that. So definitely in chemistry, and I would highly recommend you do that as well. You will oftentimes see those zeros in front of those guys. Otherwise, a lot of times things just sort of run, kind of together a lot of times. Okay. No, if you're asking, Paul, if you're asking and going from the decimal to scientific notation in terms of how to write it, the way you want to do it is the scientific notation has this sort of format, and this first guy is a number that's between 1 and 10. So that's why we had to go just one place to get us to 1.12 times 10 to the minus 1. If you did something like 11.2 times 10 to the minus 2, that would be incorrect in terms of scientific notation, as that's a number that's above 1 and 10, if that was your question. If we look at we look at the last one, which we're looking for 3 significant figures. There actually is not 3 significant figures the way it's written, which is only 2. In this case, to get us to 3 significant figures, you would need to put the 0 there. And again, that's now going to be significant because there's a decimal, and that now turns that number into 3 significant figures. Any questions on those there? So why did we go 2 places on the 825? And that was because if we had 825, the decimal would be here. If we went just one place, we would end up with 82.5, which is not a number between 1 and 10. So we had to go one more place to get to 8.25, which is a number between 1 and 10. Other questions? So the goal is, and really important, especially when you write that scientific notation, is it's very common. People always kind of use larger numbers, and it does need to be a number between 1 and 10. Can't be 10, can't be 100. Technically, really can't be below 1. It does need to basically be a number between 1 and 10. So you're really just moving that decimal until you hit a number that gets you basically 1, between 1 and 10. Other questions on that?
I have a question. What if what if it's like it's 5 and then like would number 5 and then 5.0 be the same, like for significant figures?
So say it one more time. Just 5 by itself? Is that what you're
Yeah,
asking?
5 by itself and then 5.0.
5.0. Are you asking? Say what do you want to know about those two numbers?
Like would they be like the same value?
They would be the same value. They both definitely represent 5, obviously, right? So the actual value is 5, but they are different in terms of the significant figures. So something like 5, just by itself, if it was a measurement, say 5 centimeters, for example, what that would imply is there's only really one significant figure in that number. So although the value that you would say give to somebody or report in a measurement would be 5, what you're telling somebody by only recording it as 5 in that particular case was, I'm not really sure it's 5. It might be somewhere near 6, might be somewhere near 4, but the best I could kind of guess is it's somewhere in the neighborhood of 5. but it could be as big as 6 or it could be as small as, say, 4 centimeters. When you report that same value of 5.0 centimeters, again, it does mean that this is still 5, but it has 2 significant figures. And what's important with that extra 0 is, in this particular measurement, you're telling people that, I know it's 5 and I know it's very close to 5 because on that 0 place there, or the 10th place, that is where my uncertainty lies. And you're telling people, well, it could be as low as 4.9. Maybe it's as big as 5.1 centimeters. So this type of measurement, if you had the ability to do so, is a much better measurement because you can see, you could really kind of hone in on it that I'm pretty sure it's pretty close to 5. It's 5.0. Maybe it's a little higher, maybe it's a little lower, but my uncertainty really lies over here. While if you just report it as 5 with no decimal, or you're not able to do that, you're still telling people, I think it's near 5, but there's a lot more uncertainty. It could definitely be anywhere here, or it could be anywhere here. There's a lot more room for sort of error, if you will. Maybe it's 5.1, maybe it's 5.9, maybe it's like 5.8. There's a lot more room for error, sort of happening in that case. So value-wise, they both would be 5. Significant figure-wise, the one that, for the most part, if you could go to more significant figures in a measurement, you're basically telling people that that was a pretty good measurement. I don't lose my certainty in this measurement until I get way over here, for example. Even if you wrote something like 5.0000, what you're telling somebody is, hey, I'm not really the uncertainty part doesn't come in until way over here, as opposed to our, say, 5.0, where the uncertainty is in the 10th place, and so forth. So same value, but sort of different meaning in terms of, if we're talking about measurements, which one would be, say, maybe a better measurement if you were able to do the 5.0 versus just the 5. Other questions? Okay, so that's what we did there. So we talked about this a little bit earlier. So again, here's how we would punch these into our calculator. Again, we're doing multiplication and division. We're looking for fewest number of significant figures. So again, here, if we did the top part, we're multiplying. So that is 2 sig figs. That is 4 sig figs, which means our top number should end up with 2 sig figs divided by the bottom number, which has 3 sig figs. And that means our answer should be rounded to 2 significant figures. Again, your calculator does not always give you the right number of sig figs. So we would go to here, look at the 2, and drop the rest of it and end up with 5.4. Any questions on that one? Same thing here, doing a little division. We take 8 divided by 2. Probably your calculator is going to spit out to you a 4. Again, we're dividing. So as you can see here, 3 significant figures divided by 3 significant figures means our answer should not be this, as that is 1 significant figure. We do need to put our zeros in here again to get it to 3 significant figures, uncertainty, estimated digit right there in that particular case. So again, this is just showing you that you don't always get the right number of significant figures in your calculator when you do it. You want to make sure that you round it and get it to the right number of significant figures in this case. So same thing here. If we look at the top, we most likely would do this top part first. We're multiplying, so that is 3 significant figures times 4 significant figures. That means the top number should end up with 3 significant figures, the smallest. We then would divide it by the bottom number, which is 2 significant figures. That means our answer should end up with 2 significant figures on this particular one. I think it's here. So on your calculator, it spits out 8.52. We should round it to 2 significant figures and end up at 8.53. Any questions on adding and multiplying and dividing? So multiplying and dividing, as we talked about, significant figures, least number of significant figures is where you want to go. And just to review, as I sort of jumped out there a little bit earlier, Adding and subtracting, again, we're looking at decimal places. So the answer should have the same number of decimal places as the one with the least number of decimal places. So here, when we look at all these guys that we're adding, we got 3 decimal places, 2 decimal places, 1 decimal place. Again, your calculator spits out to you this number should take you to the first decimal place, should round the number to 66.1. 66.1 has 1 decimal place, but it does have 3 significant figures if you're asked that. So keep in mind sig, figs, the decimals, what's being asked of you. So 3 significant figures, but here we would be looking at the decimal places as well. And subtracting here, again, same deal, subtracting, looking at decimal places, 2 decimal places, 1 decimal place. This is what your calculator spits out to you. And again, we would go to 1 decimal place, which would be here. Rounding with our 9, we should round up, gets us to 62.1. Again, 1 decimal place, 3 significant figures is what we're looking at here. And lastly here, adding these together, we got 3 decimal places. We have 1 decimal place. Again, if we put our calculator, we get this guy, should end up at 1 decimal place, which is here. We drop the rest of these numbers as it is 0. We end up with 104.4, which is 1 decimal place and 4 significant figures. Question again on significant figures in calculations. Again, if you have any type of exact number, you don't have to worry about it in a calculation. So if you did, use any type of definition or something that's counted, you don't have to worry about the sig figs. A common question that somebody always sort of wants to know about is what happens if we had, say, 32.1 and 12 and we're adding. So here we would end up with something like that, right, on our number. This guy has 1 decimal place. This guy has no decimal places. We would take it to the whole number and we would round to 44, which is obviously no decimal places in that particular case. Any questions on that there? Or any questions on anything we talked about today in lecture?
For solution 3,
Yeah.
Why is it centimeters squared or cubed? Sorry, instead of just centimeters.
Is it
Yeah, that one.
here?
How come
Okay.
it goes cubed?
Let me see. It might be a wrong. It is wrong. It should just be centimeters. It shouldn't be cubed.
Okay.
Yeah. So, and just in terms of the units, if we multiplied the top, we end up with centimeters squared, and then we divided by a centimeter. So that should go away, and we should end up with just centimeters. Thank you. Textbook, they make mistakes sometimes. So it should just be centimeters in that particular case. But if we were just doing the top part, that would end up with centimeters squared, right? Because the units would also multiply. One last thing, since we're talking about punching things in, again, sometimes people have a lot of numbers, that they're going to be, say, multiplying. We could write numbers maybe, let's see. And then maybe they're dividing by a bunch of numbers, maybe on the bottom, I highly recommend when you punch these things in your calculator is we're basically going to multiply the top and then divide by the bottom. And sometimes people try to punch all that into the calculator all at once. And if you're not really good with parentheses or don't put the parentheses in the right place, you're going to do the wrong math. So it's a really good idea. For example, if I was to punch this in my calculator, I would go 4.25. I would hit the multiplication button. I would times it by 3.25, hit the multiplication button. Hit 1.2, and actually I would hit equals at that point and get an answer. Then I would hit the divide button and actually divide it by just the first number, which was 22.2. I would then hit the equals button and divide it by the next number, which is 32.5, and then hit equals. So you can multiply as many numbers as you like on top. And then if you have multiple numbers on the bottom, sometimes it's best to divide by the first number, hit equals, divide by the next number, hit equals, and kind of do that instead of trying to punch it all in there. Yeah, I'll help you out with your calculator. If you have discussion, I could do it during discussion. If you don't have discussion today, just hang out at the end of lecture here and I'll try to help you, okay? All right. We'll wrap that up for lecture right now. So a reminder, what is today? Monday, that is. So those that have discussion on Monday, we'll start discussion about 7:10. Make sure you go through the discussion link that's found in the module section. If you have lab on Monday, make sure you go wherever her link is for Monday lab and make sure you go to the lab, and I'll see half of you next time. I'll see half of you in about 10 minutes. Make sure you put here if you haven't done so already.